Yeah, hello, I'm audible.
Good evening, sir.
Good evening, all of you. Wait for 1 or 2 minutes so that other students will join, and we will start within few minutes. Okay, so wait. Yeah, now I think we can start. Uh, Minashi, Hishima, and Abdul Rahman. Okay, so yeah. So in my last lecture, I discussed what is electric dipole and what is the field at equatorial point. I think axial point. We find electric field at the axial line of the electric dipole. Okay, so I'm giving a very quick revision of my last class. So in my last class, we discussed what is an electric dipole. Electric dipole. Dipole. Okay, electric dipole. So what is an electric dipole? If we put two equal and opposite charge, if we put two equal and opposite charge at a separation distance, which we consider twice of a. Okay, so this system we called electric dipole. This system we called electric dipole. And if we find the electric dipole moment, and the electric dipole moment defined as P is equals to 1 of any charge into twice of A. This is your electric dipole moment. Okay, and next we discuss what is the direction of this electric dipole moment. Electric dipole moment is a vector quantity, and what is the direction? Direction, we consider the direction of electric dipole moment from negative to positive. Okay, from negative to positive. Okay, so in this case we can consider minus j cap. Okay, so this is your dipole moment, electric dipole moment, which is defined as vector p. And after that we find the electric field on axial point of electric dipole. Yeah, electric field on axial dipole, axial line of electric dipole. Okay, so let me give you a very quick revision of the result of this electric field on axial line of electric dipole. That is electric field at or on axial line of dipole. So what we did, we take two charge, one is plus q, another is minus q, and we separated these two charge by a distance twice of a. And in that case, we consider the midpoint of this electric dipole as origin O, and the separation distance is a, and then a twice of a. Okay, and we find the electric field somewhere at this point a, this capital A. Okay, which is x distance from this capital A. The origin of electric dipole is x distance from this capital A. Okay, so in this case, what we calculated, we find the expression of electric dipole moment, electric field due to this electric dipole moment, and that electric field is vector E is equals to, what is the value of this electric field? Tell me, Minashi. It's a
2
it's a
px
yeah vector
by
P and
4 pi epsilon
yeah
px by 4 pi epsilon naught a square h square minus a
okay
square the whole
a
square.
square, the whole square. So that is the electric field due to this electric dipole, and it is axial line. Okay, now next thing, what is the direction of this field? We calculated the direction of this electric field. So here the direction of this electric field is the direction of dipole moment is somewhere like here, minus q to your plus q. Okay, and in this case we find the direction of this electric field is same as the direction of dipole. The direction of this electric field is same as the direction of electric dipole. Okay, so this is the expression of your electric field due to this dipole, due to axial line of this dipole. Okay, due to axial line of this dipole. Yeah. Okay. So next, if we consider a very tiny dipole, means very small dipole. So in that case, we neglect this this amount a. We can neglect this a because if x is much greater than a, then x square is already very greater than a square. So in that case, we can neglect this a square term. So in that case, the electric field, the expression of electric field will be E is equals to twice of P divided by 4 pi epsilon naught into x cube. This is the magnitude of electric field at axial point, at axial line, due to a very ideal dipole or very small dipole. Very small dipole. This is the electric field for very small dipole. Very small dipole. Okay, dipole. So this was a very quick revision of your electric dipole and electric dipole moment and the electric field on axial line of dipole. Okay. And today what we are going to study is the electric field on equatorial line of dipole. Okay. These two derivations are very important. The first one in the axial line and another one is electric field on equatorial line of dipole. Okay. So put the heading, that is electric field on equatorial line of dipole. Okay, so before deriving this derivation, I want to ask something to all of you, that what about your school syllabus? Okay, everyone tell me, uh, what about your school syllabus? What are the topic which is going in your school? Minashi?
Yes, sir.
Where is your school syllabus? What they are teaching you? Which unit they are
First
teaching you?
chapter.
First
First
chapter.
chapter.
And what topic? What topic there?
Electric field only.
Electric field.
Yes.
Means, so first chapter is over for us, Abdul Rahman. Okay. And Hishima, where's your school syllabus? Huh? Yeah,
Capacity.
where? Capacity is chapter number 2. And Abdul Rahman, okay, he sent me message. First chapter is over first. Okay. So I think, and one more student, Saifullah, where's
We
yours?
finished chapter, sir.
First chapter is finished. Okay.
Yes, sir.
So actually, I think we have to cover actually. So can we put a extra class on this weekend so that we can manage our syllabus? Okay. Some extra class. I think 1 or 2 class I need so that we can manage our syllabus. Okay. Are you comfortable if I put a class on weekend, means on Saturday or Sunday? Okay.
At what timing, sir?
At what time? Any time on which you are comfortable on Sunday, all of you. Sir, we have math class. Okay. On Sunday. So is on Saturday evening? Saturday evening. If you guys have time. Okay. So actually we have to consider some extra classes to cover our syllabus. Okay. So I want to finish for unit first. Okay. Over this week, I want to finish the first unit. Okay. Okay, tell me after the class that whenever you have time on over this weekend, okay, because or we can take after I think 2nd of May we can take class 2.5 hours, okay, so that we can cover our syllabus. I want to finish this chapter number 1, okay, with within this week or next week. I want to finish this chapter number 1, okay. Okay, so back to our derivation. Yeah, the derivation is electric field on equatorial line of dipole. Okay, so equatorial line. So first I'm drawing a dipole. The dipole is your, consider a charge. Consider a charge again minus q. Another charge is plus q. This is our charge plus q. Okay. Now draw a separation line. Yeah, that's your dipole, and this is separation distance. And if I put origin somewhere here, so this distance is your a, and another this distance is your a. Okay. Now we are interested to find electric field on equatorial line. What is an equatorial line? Equatorial line is the line which actually bisect this dipole, okay, which bisect this dipole at the origin, which passes through the origin, okay. And that equatorial line can be like this thing. This line we can consider if I take point here, somewhere a point here, and the line which passes through this O, and yeah, that line can be considered as equatorial line, okay. And at this equatorial line we are interested to find the electric field. Okay, so what we have to do, this is our point where we are interested to calculate the electric field. And this is your origin, and this is charge plus q, and this minus q. And what is the axial line? Axial line is something like this one. This is your axial line. So we already know what is the electric field at this axial line. Now we are interested to find the electric field at this equatorial line. Okay, is it clear to all of you? Okay. So now we can do some geometry. I can join these 2 points somewhere here. Okay. Yeah. I can draw some line. From here I am joining here a triangle and another. Yeah, I'm doing just some geometry. Yeah. Okay. So what is if this point where we are interested to find electric field, I'm putting this point C, this is point A, and this is point B. Okay, and the distance of this point C from origin is small r. This value is small r. Okay, this value is small r. From C to O means OC is your small r, and AO is your small a, and BO is also your small a. Okay, so this is all about our diagram. Okay, if this value is r, means if OC is r and AO is small a, then if I consider the triangle AOC, if I consider a triangle AOC. Okay, so in this triangle, what is the value of AC? What is the value of AC? What is the value of AC? What is the value of this AC? Means this triangle. Let me ask one thing, that is it clear to all of you that what is the equatorial line? Is it clear? Is it clear? Hishima, is it clear what is equatorial line?
Yes, sir.
What is equatorial line? Can you define it?
It is the line passing through the
Center origin of okay. And one more thing, it passes perpendicularly. Okay, this is your 90 degree. Okay, so now Next, what is the value of AC? If I consider this triangle AOC, this is a right angle triangle. And what is the value of AC? So how can you calculate this AC? By using Pythagoras. By using Pythagoras, you can find this value of AC. So what is the value of this AC? Means hypotenuse. What is the value of this AC? Is a square root of AO square plus CO square. AO square, okay, plus CO square. What is the value of AO? What is the value of A to O? Is it small a? So you can write this small a square. And what is the value of CO? Is small r. So now you calculated what is the value of AC. AC is under root A square plus R square. Okay. Is it clear? It's a very easy. I just applied the Pythagoras theorem and we easily find the value of this AC. So I am writing here the value of AC is under root R square plus A square. Okay, under root R square plus A square is the value of this AC. Okay, so that is under root R square plus A square. Okay, and what is the value of this BC? What is the value of this BC? Search. Okay. What is the value of this BC? BC. What is the value of this BC? Okay. Shafullah, what is the value of BC?
This is an equatorial triangle, right?
Yeah. No, it's not equatorial triangle, but it's a. This is perpendicular. This is your perpendicular. This is RA. This is similar to this AOC and COB are similar triangles. Okay. So this is if this angle is theta. So this value is
R
already
square plus A square.
R
whole
square
root.
is plus A square. Yeah. Under root R square plus A square. So these two values are equal. R square plus A square. Okay. These two values are equal. Okay. So now we have done some geometry. Now next part is the electric field. If I talk, what is the electric field? What is the direction of electric field due to these two charges? So due to negative charge, the electric field will be in this direction. In this direction, due to negative charge, E minus, and due to positive charge, the direction of electric field is somewhere here. Is somewhere like this. Yeah, this is electric field due to E plus. Is it clear? Okay. The electric field E minus due to your negative charge and electric field E plus due to your positive charge. The electric field due to positive charge is outward and the electric field due to negative charge is your towards negative charge. Okay. And due to positive charge, it's far away from the positive charge. Okay. So this is all about geometry. Now we have to find the net electric field. We have to find the net electric field. For that, we have to resolve these electric field vectors. Okay. So this is 90. So we can consider this is angle theta. Okay. And if two sides are equal, so this angle is also theta. Okay. Now next part, if I draw a line parallel to AB, if I draw a line parallel to AB, okay. So in this case, this angle is also theta. Let me use different colors so that you can get a clear idea. This angle is also theta. Okay. And this angle is also theta. Okay. Now next part is if this electric field E plus, if I resolve this electric field in component terms, then the E plus have two components. So this component, see the blue color one is your E plus. What's the component? It's a vertical component. So vertical component is E plus sine theta. If you have any question, then ask. This vertical component is E plus sine theta. And what about this horizontal component? Horizontal component is again E plus cos theta. Okay, it's all about geometry. Once you done with the geometry, then other part is very easy. Now we have to again take the resolution of this vector E minus. It also have two component. Okay, it also have two component. So I am taking different color for E minus. It's okay, E minus. Okay, so take E minus with, yeah. So E minus has two component. One is your again this is your vertical component. Vertical component is your E minus sine theta. E minus sine theta. Okay, E minus sine theta. Yeah. So it has two component. One is E minus sine theta, and it's a horizontal component which is E minus sine theta, and its horizontal component which is E minus cos theta. Okay, this is all about the diagram. Okay, is it clear or you have any doubt? Okay, we have two component of electric field. So the next part is what is the value of this E minus, the electric field due to minus charge? What is the value of this E minus? So what is the value of E minus? You can find the value of E minus. The value of E minus is 1 over 4 pi epsilon naught. The value of E minus is 1 over 4 pi epsilon naught q divided by, what is the distance from this E minus, means minus q, to point where we are finding the electric field is C, and that is under root r square plus a square. Under root r square plus a square the whole square. Okay, so put the equation number 1. Next, the value of E plus. What is the value of E plus? E plus is 1 over 4 pi epsilon naught, that is same q q divided by, and again the distance is your bc square, and bc you already know it's under root r square plus a square. So that is again your under root r square plus a square the whole square. R square the whole square. That is equation number 2. So you can see that here E plus and E minus are equal. E plus and E minus are equal. E plus and E minus are equal. And what about the component? The horizontal component is E plus cos theta and E minus cos theta, and vertical components are E plus sine theta and E minus sine theta. Okay. Now note it down. Then I will go to the next part of this derivation. Note it down, and if you have any question regarding geometry, then you can ask. Okay. I will again discuss the geometry. If anyone has any problem, then I can again discuss this geometry. Note it down. Tell me when you're done. It's all about resolving the vector. The figure is clear to all of you. Tell me yes or no.
Yes, sir.
And you, Hishima,
Yes, sir.
all components are clear, na? Vertical and horizontal. And you, Minashi?
Yes, sir.
Okay. And Maziha, is it clear to you? Maziha?
Yes, sir.
Okay. Yeah. Okay. Okay, so I'm going to the next slide. Okay, so I think all of you done. Okay, so I'm going to the next slide. So here you can see that the magnitude of this electric field E minus and E plus are equal. The magnitude of this electric field means E minus, they are different in direction, but their magnitude are equal. This is equation number 3. This is equation number 3. Okay, so we have two electric field, one along y direction and other along x direction. There are two electric field now. Means as I draw, means we are calculating actually electric field at this point, and this is your negative q charge and this is your positive q charge, and due to a negative q charge your electric field in this direction, and due to positive q charge the electric field is your in this direction. These two direction electric field are na. This is your E plus and this is your E minus. What we did, we resolve this electric field. The horizontal component are E plus cos theta, E minus cos theta. These are two electric field. Okay, horizontal direction, and the vertical are E plus sine theta, and again in this direction E minus sine theta. Okay, these are two thetas and theta. So this is all about the direction. Okay, okay. So two direction on horizontal axis, these two electric field E plus cos theta, E minus cos theta. On vertical, E plus sine theta, E minus sine theta. Okay. So now let me find the net field along y-axis. The net electric field along y-axis. Y-axis. What is the net electric field along y-axis? So that is EY. Net electric field along y-axis is EY is equal to E plus sine theta, and they are opposite in direction. E plus sine theta and E minus sine theta are exactly opposite to each other. Exactly opposite to each other. So in that case, so E plus sine theta, that is minus E minus sine theta, because they are exactly opposite to each other. Okay, and from equation 3 and from equation 3, you know, E plus is equal to E minus. E plus is equal to E minus. So in this case, the net electric field along y-axis is 0. The net electric field along y-axis is 0. Is it clear? Because E plus is equal to my E minus. This E plus is equal to E minus, and sine theta is sine theta same, and they are equal in opposite. So in this case, they will cancel each other. So you will get no electric field along y-axis. You will get no electric field along y-axis. Okay. Up to now, what we have calculated, we just draw this diagram. We did some geometry and we find E plus and E minus, and we calculated the electric field along y-axis. What we find electric field along y-axis is 0. Okay. Okay, is it clear? Now the next part of this derivation, we are going to calculate the electric field along x-axis. Now we are going to find the electric field along x-axis. Now the electric field along x-axis. Yeah, somebody asked me a question. Sir, how is E minus equal to E plus? Yeah. So that actually I showed in your equation number 3. In equation number 3, yeah, this is E plus equal to E minus. How? The value of this E minus is 1 upon 4 pi epsilon naught q upon under root r square plus a square, the whole square, means q upon r square plus a square, and E plus is again 1 over 4 pi epsilon naught q over r square. So these two quantities are equal now. These two quantities are equal. 1 is equal to 2. The magnitude of E plus and E minus are equal. What the difference? They have different directions. We already draw geometry for directions. We draw horizontal and vertical component. Okay, so if we calculate the vertical components, in that case we can see the electric field due to positive and negative charge, and the vertical component are exactly cancelling each other. Yeah, this is your E plus sine theta, E minus, they are cancelling each other, and the magnitude of E plus is equal to E minus. So that's why the electric field get cancelled out. Is it clear? Abdul Rahman, is it clear? E plus is equal to E minus, the magnitude. not in direction, the magnitude. Okay, so E plus is equal to E minus in direction. Now next part is horizontal axis. We are calculating the net field along y-axis. Net field along y-axis. Y-axis. What is the net field along y-axis? Is Ey is equal to E plus x-axis, not y-axis. I already calculated. So this x-axis, what is the electric field at x-axis? Tell me. Ex is equals to Minashi, tell me electric field at x-axis. Yeah.
Ex is
What is
equal to E plus cos theta minus E
theta?
minus cos theta.
Yeah, but not minus because they are in same direction. See the arrow? They are in same direction. If I consider the this figure, so you can see that both field are in same direction. Here they are in opposite. These two field are in opposite direction. Okay, these two are opposite, but these two are in same direction. Okay, direction is same. It's in negative x direction, but the direction is same. So in this case, they will get added. We can add these two. So this Ex is equals to is E minus cos theta, the electric field due to minus charge, plus the horizontal component of electric field due to plus charge is again E plus cos theta. In this case, they get added, and we can write this equation number as 4. Okay, 4. Or if we substitute E minus is equals to E plus, means this equation number 3 in 4, if we substitute equation number by using 3 in 4, so what we can have, we can say that this electric field along x axis is equal to E plus cos theta, because both are equal, so we can put E plus is equals to E minus, so we get E plus cos theta plus E plus cos theta, that is equal to 2E plus cos theta. Okay, that is equal to 2E plus cos theta. That is equal to 2E plus cos theta. Put the equation number 5. Okay, now if we substitute this value of E plus from equation number 2, we can substitute the value of E plus into equation number 5. So we will get a expression. So substituting equation number 2 in equation number 5, what we can have, that is Ex is equal to twice of, what is the value of E plus, is 1 over 4 pi epsilon naught q divided by r square plus a square. R square plus a square, and one more term which is cos theta. This is your electric field, but we have one unknown parameter, that is theta. We want to exclude theta from this equation. So for that we have to find what is the value of cos theta. We can easily find the value of cos theta. Okay. Yeah. So we can easily find the value of cos theta. How we can find the value of cos theta? Wait a second. Yeah. How we can find the value of this cos theta? From this triangle. From this triangle, we can find the value of cos theta. Here you can see this. If you consider the triangle AOC, see the diagram, AOC. Here we can find the cos theta. What is the value of cos theta? That is equal to base means AO divided by your hypotenuse. What is the hypotenuse? It is under root a square plus r square. So what is the value of this cos theta? Is equal to base, which is a divided by under root r square plus a square. This is the value of cos theta. Is it clear? Note it down, the value of cos theta. So is it clear to all of you now? Or do you have any doubt? It's very simple. We just consider the triangle, right angle triangle, which is AOC, and from here we find the value cos of theta. So the value of cos of theta, I am again rewriting the expression of cos theta. The value of cos of theta is equal to a divided by under root a square plus r square. Now substitute this value of a square plus r. Substitute this value of cos theta here, so we will get the exact result of electric field at equatorial line of electric dipole. Okay, so substitute this value of ex, the value of cos theta in this expression. So from here we can have that is 2 into 1 over 4 pi epsilon naught q divided by r square plus a square into a divided by under root a square plus r square. Okay, now we can do some calculation. We can rearrange this term. So here the power is 1 and here the power is r square plus a square power 1 by 2. So I'm just removing the square root and putting a square plus r square the power 1 by 2. Okay, as you know, if we multiply then power get added. So now you can get the value 1 over 4 pi epsilon naught q into 2a divided by r square plus a square the power 3 by 2. Is it clear now? 1 plus 1 by 2 is 3 by 2. And where is the electric dipole moment in this equation? Where is the electric dipole moment? You can see the electric dipole moment. It's a q into 2a. It's a q into 2a. It's a q into 2a. So we can replace this q into 2a by capital P. So in that case, the electric field is equal to 1 over 4 pi epsilon naught P divided by r square plus a square the power 3 by 2. It's our electric field due to our due to dipole at this equatorial line. This is the electric field. Okay, this is the electric field. Okay, so this is your electric field along x-axis. This is your x-axis, electric field at x-axis. Okay, now the net electric field is along, if we add this electric field, net electric field, actually this is the net electric field, because as you know the net electric field along y is 0, so the remaining is your x. So that is equal to 1 over 4 pi epsilon naught P divided by r square plus a square power 3 by 2. Now what about the direction? What about the direction? Is it parallel to electric dipole or it is anti-parallel to electric dipole? What is the direction of this electric field? Is it parallel to electric field or it is opposite to the electric field? Ishima, can you tell me the direction of this electric dipole? So I'm going to the diagram. Yeah, this is our diagram. So here, what is the direction of this electric field? Here, what is the direction of this electric field? The direction of electric field is from, sorry, first tell me the direction of electric dipole. It's from negative to positive.
Negative to positive.
So this is your along positive x-axis. This is the direction of electric dipole, capital P. And the net field is along in this direction. Okay, so this is your net electric field. So in this case, the electric field and electric dipole are opposite to each other. In this case, the electric field and electric dipole are opposite to each other. They are not along the same direction. They are opposite to each other. Is it clear? The direction of dipole moment is from negative to positive, and electric field is along your negative x-axis. So we have to put a negative sign to get the exact value of electric field with direction. So net electric field is, so here you can see in the diagram, if this is our negative q charge and this is our positive q charge, so the direction of dipole moment is from negative to positive, and the net electric field at equatorial line, this is our equatorial line, the direction of electric field is along this direction. This is our electric field, net electric field, and this is our dipole moment. So in this case, the direction of the electric field with direction is vector p divided by 4 pi epsilon naught r square plus a square the power 3 by 2, and we have to put a minus sign. So this is the expression of our electric field. Okay, any question? So you can write one more line here. So on equatorial line, on equatorial line, the direction of electric field. Yeah, one question, sir, why minus? Because they are parallel. No, they are not parallel. I'm writing the statement, they are actually anti-parallel. On equatorial line, direction of electric field opposite to the direction of electric field, the direction of electric field is opposite to the electric dipole moment, to the dipole moment. Okay, dipole moment. Okay, so if you have any doubt, I'm again going to the figure. Now see in this figure, the direction of electric field is again in this direction, the net electric field. Okay, the net electric field along negative x direction, and the direction of dipole moment is along positive x direction. So in this case, they are anti-parallel. The electric field is along in this direction. Okay, and the dipole, the direction of dipole is, this is your electric field, and this is your dipole moment. Okay, this is your dipole moment, is your positive x-axis, and electric field along negative x-axis. So in this case, both have anti-parallel directions. Electric field is along negative x-axis and dipole moment along positive x-axis. That's why we get a negative sign here. If we when we find the electric field along axial line, then in that case the electric field is same as electric dipole moment, but in this case it's opposite to the dipole moment. Okay, now take a note. Okay, take a note of this derivation. Yeah, just write it down, everything. It's an important derivation. Then we will go to our next topic. I will give you a assignment related to this electric dipole moment, electric field at the axial line of electric dipole, and electric field at the equatorial line of a dipole. That you have to complete, that you have to finish that assignment, so that you will get a clear idea about this topic, electric dipole. At least you have to take practice 2 times of these 2 derivation. Okay, After that, I will compare what is the difference between electric field due to axial line and equatorial line. I will take a proper difference. I will show you a difference. What are the difference? Put it down. Okay. Are you guys done?
1 minute.
Okay. Okay.
Done, sir.
Okay. Everyone done? Maziha done? Maziha. Okay. Okay. So now, yeah. So if we talk about the ideal size of ideal dipole approximation, so means ideal dipole approximation means if the size of dipole is very small, size of dipole is very small. So in this case, what the change in this expression? What will be the change in this expression? So again, if the size of the dipole is very small, so in that case, same as previous case, if the ideal dipole approximation, yeah, any message? Sir, we can write 1 over 4 pi epsilon. Yeah, you can write 1 over 4 pi epsilon not as capital K. Okay. Okay. But I think it's better to take expression of 1 over 4 pi epsilon. Okay. But you can also write K. Okay. But you can also write K. But it's better to use 1 over 4 pi epsilon because the value of K we consider only for numerical purpose. That will be easy. Okay. Okay. Both are correct. I'm not saying this is wrong, but it's better to use 1 over 4 pi epsilon. Okay. Now, ideal dipole approximation. It says that when A is very less than R, means this A, which is the separation distance from minus Q to plus Q, this twice A means this twice A, this is A, and again this is A. If this A is very small in comparison to R, okay, this R is much greater than this A, means dipole is very tiny, and you are considering A is far greater than in comparison to A. So in that case, we can take this R square plus A square as your R square. In that case, the electric field is equal to minus vector P divided by 4 pi epsilon naught. What will be the value? 4 pi epsilon naught. This will be R square the power 3 by 2, and here 2 and 2 get cancelled out. So the net electric field for this tiny dipole is minus vector p divided by 4 pi epsilon naught r cube. 4 pi epsilon naught r cube. This is your electric field for your very small dipole. And here you can again see the electric field due to a dipole is 1 over r cube. Okay, the proportionality of electric field due to a dipole is always 1 over r cube. And for a point charge or single charge, the electric field is proportional to 1 by r square. Always remember the proportionality of electric field due to a point charge or mono charge is 1 over r square, but the proportionality due to a dipole is 1 over r cube. Okay, so this is electric field due to a very small size dipole, very small size dipole. Okay, note it down. This is your ideal dipole approximation. Vector p divided by 4 pi epsilon naught r cube. Done. Sir, what is r in figure? Small r, yeah, small r, as I mentioned in figure. Yeah, that figure you are asking. This figure. Okay, this is smaller. This distance, this distance is your small r, na? As I showed in figure. This is your small r. Okay, this is your minus q. This is your plus q. And the point here we are calculating the electric field at this equatorial line. This is your r. And this is your small a. Okay. Is it clear? Abdul Rahman, is it clear to you? Yeah, okay. So this is your ideal dipole approximation. Next, I'm going to differentiate what is the difference between electric field on axial and equatorial line. What is the difference? So let me discuss what is the difference. So write a small note. Difference between electric field, EF means electric field, on axial and equatorial line. Equatorial line. Okay, so at the axial line, the electric field is defined as twice of vector p divided by 4 pi epsilon naught r cube. In this expression, I am using r cube because we can replace x by r. I choose actually in derivation I choose x, but you can also choose r instead of x. And this is expression for a small dipole. This is expression for a small dipole, not that one. If we apply the condition when your x or r is much greater than a, so in that case the electric field at axial line is 2p over 4 pi epsilon naught r cube. And the electric field at equatorial line, the electric field at equatorial line, that is minus vector p divided by 4 pi epsilon naught r cube. So here you can see the two differences. Okay, Saifullah, can you tell me what is the first difference you can find from these two expressions?
Axial is twice of equatorial.
Yeah, it's a twice of equatorial. And one more thing, the direction. The one thing is it's a twice of equatorial. Axial, if we talk about magnitude, so magnitude of electric field at axial line is equal to twice of magnitude of electric field at equatorial line. And the another thing is the direction. Both are in opposite direction to the electric dipole. At axial line, the electric field is same as electric dipole moment, but at equatorial line the electric field is opposite to the dipole moment. Okay, so here the first difference is direction of electric field. Take a note small. The direction, first related to direction of electric field. The direction of electric field on axial line is same of that of dipole moment okay, on equatorial line, it's opposite to the dipole moment. It's opposite to the dipole moment. Okay, note it down. The first point, which is direction of electric field on axial line, is same of your dipole moment, and at equatorial line it's opposite to the dipole moment. Okay, and the next part, second difference, is the E axial is equal to twice of, okay, if I talk about magnitude, not direction, so we can neglect this negative sign. So we can write this is 2p over 4 pi epsilon naught r cube, and the electric field at equatorial line is equal to p upon 4 pi epsilon naught r cube. So here you can write as E axial is equal to twice of E equatorial. Magnitude. The magnitude of electric field at axial line is equal to twice of electric field at equatorial line. So you can get the ratio, that is E axial divided by E equatorial is equal to 2 by 1. Okay, so write it down, this difference. Okay, this difference. There are 2 points related to the difference. Okay, okay, so this is all about electric field at the different point of dipole. We calculated the expression of electric field at the axial point, also at equatorial point. We define what is dipole. We also define what is electric dipole moment. So this is all about electric dipole. Okay, electric dipole. You have two long derivation related to electric dipole. Okay, so that is all about electric dipole. Everything I told you, but related to electric dipole. Okay, do you guys have any question related to electric dipole or electric field due to this dipole? If anyone have any question, then they can ask. Now I'm going to discuss the next topic, which is electric field lines. So the next topic, put the heading, that is your the electric field lines. The next topic is your electric field line. Electric field lines. Okay, electric field lines. I already gave you very small idea related to this electric field line in my previous lecture, but today I will discuss in brief what is electric field lines. Okay, so electric field lines. If I put a charge q, suppose if I put a charge q, then there is electric field around this positive q charge. There is electric field around this positive q charge. Okay, so electric field lines basically gives the geometrical explanation of electric field around this charge q. Around this charge q, what are the electric field? Because it's easy to understand what is the electric field if we take the geometrical interpretation or pictorial representation of electric field. Okay, so that is basically the electric field. The definition of electric field lines is uh, if write a small definition, that is electric field lines are curved. Electric field lines, electric field lines, this is a very small definition. Lines are curved such that curve such that electric field lines are curved such that the tangent to them, the tangent to them gives direction of electric field, gives direction of electric field. Electric field. Okay, so this is a small definition related to your electric field lines. So if I draw a curve, suppose I draw a curve, this is our curve, suppose. Okay, this is electric field lines. At this curve, if I draw a tangent, suppose I draw a tangent at somewhere here. Yeah. Suppose I draw a tangent somewhere here. Yeah. Suppose I draw a tangent somewhere here, Yeah. So this is a tangent over this curve, and this tangent will give the direction of this electric field. So here, this is electric field. This is the tangent over this point. Okay. So this will give you the direction of this electric field. If I'm interested to find electric field at this point, so I can draw a tangent over here. So again, the another tangent will give you the electric field, the direction of electric field line at this point. Okay. Yeah. So this is all about your electric field line. Yeah. So this is your electric field. Okay. So at this point, if you are interested to find electric field, so that will give you somewhere here. So this is okay. Yeah. So what is the electric field lines? So electric field lines, if you take the tangent over this electric field line, that will give you the idea about electric field. Okay. So one more point you can write related to this electric field lines is that electric field lines are geometrical. These are geometrical and pictorial representation of electric field. Representation of electric field. Okay. So there are some properties related to this electric field line that actually are important. So next, right, the properties of this electric field lines. I will discuss some properties of this electric field line. The next heading is properties of electric field lines. Electric field lines. Okay, now I'm going to tell you one more important thing, that actually the concept of this electric field lines is pure hypothetical. If you consider a charge plus q, so no experiment ever done that it verifies the electric field around a positive q charge. Okay, but this is a hypothetical concept. Due to this hypothetical concept, we get the clear idea of electric field. We get the clear idea of electric field due to this electric field line, due to this concept of electric field lines. Okay, so that's why this concept of electric field lines is important, because it will give you an idea of electric field. Okay, or you can say geometrical representation of electric field. But this is a pure hypothetical concept. Okay, magnetic field lines they exist, but the electric field lines is a pure hypothetical concept. Is it clear to all of you? Okay, we consider this concept to better understand the electric field. Okay, this is an important point which I discussed with you. So the next part, which is properties of electric field lines. So the first property, as I already told you, already told you, that tangent to electric field lines gives the direction of electric field. So note it down. The first point is the tangent to electric field lines, electric field lines, okay, give direction of electric field, give direction of electric field, give direction of electric field. Okay, so if I draw a curve, again I'm repeating, if I draw a curve and if I am finding the direction of electric field, so I can draw a tangent over here. So this is your electric field. If I am considering the point here, so we can draw a tangent over somewhere here, so that will give you the direction of electric field. Okay, at this point and over this point. So the tangent over curve will give you the direction of electric field. Tangent to electric field lines give you direction of electric field. Next important point related to this point one, note a small note. It's related to point number one, and that's very important, that two electric field lines never intersect each other. Okay, that's a very important point. Two electric field lines never intersect each other. Okay, never intersect each other. Why they never intersect each other? Two electric field lines never intersect each other. Why? Because if two electric fields suppose intersect each other, suppose I am taking a electric field line in this direction, and I am taking electric field line in this direction. So what happened if these two electric field line suppose intersect each other? So in that case, the first curve, suppose this first curve have at this point, if I take a tangent, then the direction of electric field line in this direction, and over this curve, the direction of, if I take a tangent, then the direction is like in this direction, E1, E2. So at a single point A, there are two direction of electric field. That's not possible actually. At a single point, the direction of electric field is in only one direction. Okay, but here if they intersect each other, then what happened? There are two direction of electric field lines. That's not actually possible. So that's why two electric field lines never intersect each other. Okay, so you can write as after this diagram that at point A, that at point A, you can write as at point A, at point capital A, two direction of field lines, two direction of field lines, which is not possible. So electric field lines, EFL, electric field lines never intersect each other, Is it clear, or you have any doubt? Okay, Minashi, why two electric field are not never intersect?
Because it will have two directions.
Minashi, can you tell me why two electric field line never intersect each other?
Because it will have two directions.
Yeah, because if we take tangent over this electric field line, then that will give you the direction of electric field, and at a single point, the two direction of electric field line is not possible. The two direction of electric field line is not possible. So that's why two electric field line never intersect each other. So this is your point one, and one note related to this point one. Okay, note it down, then I will discuss the next part. Note it down, the first point. Yeah, the first point, then I will discuss the second point. There are basically 8 properties of these electric field lines. 8 properties of these electric field lines. After studying these electric field lines, you will get the very clear idea of electric field. Actually, the geometrical representation of electric field. Okay. 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 So next point. Have you guys done? Noted down all the points? The first point, sorry, not all the points. Okay. So next point, the point number 2, which says that the relative density of electric field line gives the strength of electric field. Okay. So if the electric field line are very close to each other, then in that case we say the electric field is a strong electric field. There is a strong electric field. If the separation distance between two electric field line is more, so we can say that this is the weak electric field. So the density, means relative density, gives the strength of the electric field. That is the that's your second property, which is the relative density. That is relative density. Yeah, relative density. Okay. Or you can say separation. Relative density, or you can say separation of field lines. Separation of field lines gives strength of electric field. Gives strength of electric field. Okay. So actually in the region of a strong field, the field lines are very close to each other. In the region of weak field, the electric field line are are comparatively far apart. So you can write one more point. In region of a strong field, the electric field lines are the electric field lines are close, and in region of weak field and in region of weak field they are comparative far apart. They are comparative far apart. Okay, so let me draw. Suppose this is a region of electric field line. Okay, this is a region of electric field line. Yeah, and there is another region of electric field. This is another region of electric field. Okay, so this is the first region and this is your second region. This is your first region of electric field and this is your second region. Okay, so can you tell me, Hishima, can you tell me which region has strong electric field? Take a look of this statement and give me the answer. Which region has a strong electric field? Region 1 has a strong electric field or region 2 has a strong electric field? Can you tell me?
The first reason.
Yeah, the first region has a strong electric field because as I wrote in my statement, that they are very close to each other. They are more dense. So you can write this: the electric field in first region is greater than electric field in second region. Okay, so this is property number 2. Where the electric field lines are very close to each other, in that case, that region will give you a strong field region. Okay, strong field region. Okay, so have you ever think that why we are studying this electric field, why it is important? Is there any daily life application of this electric field? Okay, is there any daily life application of this electric field? Yeah, because after studying this electric field, we will get the idea of an electric current, that we actually use electric current. The whole syllabus of your 12th means when you read from chapter 1 to chapter up to Maxwell's equation, means the whole electrodynamics theory. When you complete the whole electrodynamics theory, you will get the clear cut idea of the whole development of physics and engineering from a charge to a generator, alternating, how we discover, how we find alternating current. That's actually very cheap. If we haven't discovered the alternating current, the theory of the unification of electric field and magnetic field, then up to now we haven't designed the alternating current, because the alternating current is one of the best discovery of the human, because the electricity is cheap. Okay, you can get a 24-hour electricity. Okay, so that you can use your laptop, your computer from this electricity. Okay, so that's why it is meaningful to study this electric field, electric current, and after that magnetic field, and then the Faraday's law, Ampere's law, and after that finally the Maxwell's equation, which gives the unification of electric field and magnetic field. That's very important actually. These all things are connected. The whole electrodynamics is totally connected to each other. Okay, so that's why it's important. As if you consistently read and understand the electric field, and after electric current, and after magnetic field, and after that Ampere's law and Faraday law, then you will very enjoy the whole syllabus, and after Maxwell equation. Okay, the whole electrodynamics. Okay, how how things get developed from the discovery of charge to alternating current. Okay, that's actually interesting theory, but just you have to just work out on the mathematical part. But once you get familiar with this mathematical terminologies, then it's very easy to understand this theory. Okay, this is the theory. Basically in physics we have very few major theories. Actually in your 11th you studied one of the major theory, which is classical theory, means Newtonian physics, in which the whole physics is governed by this Newton's law of motion. And the physics behind charges, means the physics behind electrical charge, motion of charge, acceleration of charge, and this the physics behind is the Maxwell's equation, or you can say electrodynamics, electromagnetism. Okay, there is another physics which we call like modern or quantum physics. In that case we studied the microscopic world, okay, through Schrodinger equations. That's actually quantum mechanical picture of the universe, our universe. Okay, there is one more picture of the universe, is your relativity. Okay, when a particle moves with very high speed, then all laws of physics deal with the special theory of relativity that was actually given by Einstein. Okay, so this is all about the physics. The whole syllabus of your this class is very interesting, is very advanced and very interesting. Okay, you will get uh, all the physics in a very compact form, okay, so I think you will enjoy the whole physics. Okay, now back to our point, which is our properties. So now the third property, okay, give me a small some examples of this statement. Suppose I consider a charge q plus q. In this case, suppose the electric field lines have 1, 2, 3, and 4. Suppose there are 4 electric field lines due to this plus q charge. Okay, so if I double the charge, then electric field line are also get doubled. Okay, when the magnitude of charge is plus q, then the number of electric field line are 4. And when I double the electric charge, then in this case we get 8 number of electric field line. 1, and another is 2. Okay, 1, yeah, 2, yeah. So in this case you have the electric field lines are, these are 3, 6. Okay, and one more. The number of electric field lines are 8. In this, number of electric field lines are 8. So whenever we double the magnitude of charge, and then the electric field line gets doubled. Okay, suppose another example. Suppose if I consider a charge plus 2 coulomb, and in this case it has only 2 electric field line. Okay, so if I increase this charge by this amount 8 of c, then how many numbers of electric field line in this case plus 8c? Saifullah, can you tell me, Mohammed Saifullah, can you tell me how many numbers of electric field line due to this plus 8c charge? If plus 2c has 2 electric field lines.
8.
Yeah, again it's 8 because it's 2 and we increase 4 times. Okay, so again the electric field lines is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now next property, that is property number 3. This is third property. Okay, so the electric field lines are originate from a negative charge and terminates as electric field line originate from a positive charge and terminate at negative charge. Electric field line field lines originate from positive charge and terminates at negative charge. Okay, electric field lines originate from positive charge and terminate to negative charge. Okay, so means the direction which you consider like positive to negative. Okay, so this is the direction of field, positive to negative. Originate from positive direction, positive charge, and terminate to negative charge. One more property. There are total 8 property, and the fourth property is electric field lines are continuous curve. Electric field lines are continuous curve. Okay, so these are 4 properties. Okay, today I am stopping here. These 4 property, and next 4 property I will discuss in my next lecture, means on Wednesday. Okay, on Wednesday I will discuss next 4 properties. Okay, so what we studied today we studied we find the expression of electric field at the equatorial line of a dipole. That's a long expression, long derivation. We completed that derivation, and after that derivation we studied what is electric field lines, and we studied the 4 properties of electric field lines. Okay, so today I am stopping my class here. The next class will be on Wednesday, same time, I think 6:30. Okay, sir, when is extra? Yeah, in weekend I will put a extra class on weekend or Friday or after Wednesday. I will discuss the timing of extra class. Okay, maybe on these 3 days I will consider one, means on Friday, Saturday, or Sunday I will take one more extra class, almost 2-hour extra class. Okay, so that's why we can manage our. Okay, Friday is fine. Okay, so if everyone is okay with Friday, then we can put extra class on Friday. Okay, we can, all of you, are you agree with the timing of Friday? Means on Friday we can consider extra class. Minashi, Hishima, Saifullah.
It's okay with me, sir.
It's okay. Okay, so I'm closing this class at this time. See you guys on Wednesday.
Thank you, sir.
Okay, welcome.